All right, let's just dive right into this explainer. Today, we're going to investigate the fascinating and honestly a bit mind-bending mathematics behind how developers actually build automated lie detectors for artificial intelligence. I mean, this is an absolutely high-stakes area of AI right now, and understanding the math behind it, it's completely essential. Because look, we've all been there, right? We've all seen an AI confidently spit out a complete factual error. Take this hallucination, for example, claiming Charles Lindbergh walked on the moon in 1951. I mean, we all know Neil Armstrong did that in 1969, yet here's the AI presenting this absolute fiction as a completely confident, undisputed fact.
So, that brings us to the central mystery we're unpacking today. How exactly do developers catch these AI hallucinations when the model sounds, well, 100% confident? How do we mathematically catch these errors and evaluate an AI's true certainty behind the scenes?
Here's our roadmap for the explainer today. We've got 1. The AI hallucination problem, 2. Uncertainty and confidence explained, 3. White box quality estimation, 4. Black box quality estimation, 5. Tunable metrics and Comet QE, and finally 6. Calibrating AI confidence. Okay, let's get right into it. Starting off with section 1, the AI hallucination problem, detecting confident lies. Let's start at the scene of the crime to establish why an AI system generates these hallucinations in the first place. The ultimate goal for developers here is to build automated mechanisms that can actually detect when a model is secretly unsure about its own answer. Moving right along to section 2, uncertainty and confidence explained, the 2 types of doubt. You see, to interrogate an AI effectively, we first have to understand the 2 very different types of doubt it experiences during text generation. Because, spoiler alert, not all uncertainty is created equal. The contrast here is really fascinating. First, you have aleatoric uncertainty. Think of this like a static-filled wiretap that you just can't fix. It's inherent, irreducible noise right there in the data itself. But then, on the flip side, you have epistemic uncertainty. This simply means our model hasn't seen enough evidence yet. It's a lack of knowledge due to missing training data, which, and this is the key part, is something we can actually reduce by teaching the model more. So how do we track this? Well, we mathematically measure this confusion using something called Shannon entropy. It's basically an uncertainty equation calculating the weighted log probability across all possible generated sequences to measure the disorder of a model's prediction. Put simply, entropy spikes really high when the AI acts like a conflicted witness on the stand, splitting its story evenly across multiple different answers instead of just committing to one single outcome. Which brings us to section 3, white box quality estimation, interrogating the AI's brain. If we really want to understand that confusion we just talked about, we have to look inside. If we have direct access to the AI's internal neurons, we can run a white box interrogation to see exactly how confident it really is about its outputs, literally token by token.
But we run into a fascinating problem here. Sometimes the model actually isn't confused at all. It's just trying to decide between perfectly valid linguistic synonyms. Standard probability scoring heavily penalizes models for this. So, developers use modified sequence probability. This metric elevates the score of valid ambiguous synonyms by summing their dominant token probabilities, basically to prevent unfairly punishing the model just for having a really good vocabulary.
To put that into perspective, imagine words like at a 0.45 probability and such at 0.30 sharing the top probability mass. We group them together as dominant tokens. So instead of the word such getting the kind of mediocre score of 0.30, we sum those dominant probabilities together. This lifts the AI's confidence score to a combined and highly viable 0.90. It's a total game changer for evaluating the model fairly. Another thing we do inside the white box is track the k-nearest neighbor quality penalty. Here, the model computes the Euclidean distance to its nearest training data neighbors. Basically, we are checking if the AI's hidden state vectors are wandering off into unfamiliar territory far away from its trusted data. A large distance, say 1.0, explicitly tells us, hey, this model has high epistemic risk and is probably generating anomalous, hallucinated text. Now, white box methods are incredibly powerful, right? But that leads us to a massive roadblock in the modern tech landscape. What if the AI's brain is completely sealed off from us behind a corporate API? What if we literally just can't see its internal math? That takes us to section 4, black box quality estimation, the outside stakeout. When we can't see inside the model, we have to rely on surveilling its behavior entirely from the outside, using only the raw inputs we give it and the text outputs it gives back. One really common surveillance tactic for this is black box sampling. This is basically interrogating the AI by sending it the exact same prompt, say 10 times in a row, and counting how often a specific target output repeats. You just divide the target count by the total query trials. So if the phrase "let's go" is generated 6 out of 10 times, boom, that's an estimated 60% confidence. It's effective for sure, but doing this requires a ton of computational power and introduces a whole lot of latency. So the crucial takeaway here is that we need smarter external tactics. Enter perturbation-based tracking. In step 1, we slightly perturb the input, like changing the name John to Sam. Step 2, we translate those altered sentences. And step 3, we align the translations to check if unrelated words erratically fluctuate. We can literally catch an AI in a lie if a completely unrelated translated word suddenly destabilizes and shifts just because of that one tiny input change. Moving into section 5, tunable metrics and Comet Kiwi, the expert profiler. So, because rigid math rules and strict word matching can sometimes fail to capture true semantic meaning, we bring in an expert profiler, tunable metrics. This is where quality estimation gets truly advanced. So, what are they? Tunable metrics are actually machine learning models trained on human rankings to evaluate other AI systems. They do this by dynamically checking semantic vector similarities. Basically, they use embeddings to understand that translating the word house into building is actually a highly accurate response, rather than blindly flagging it as a mismatch error just because the literal characters don't match. A prime example of this is Comet Kiwi. It's a neural model for evaluating machine translation without needing references. It concurrently predicts a continuous sentence level score while simultaneously outputting binary word labels, like okay or bad. It's effectively mapping out the exact locations of the hallucinations, checking the work without needing the answer key. Finally, section 6, calibrating AI confidence, judging the judge. To wrap up our investigation today, we absolutely have to make sure our automated lie detectors are actually telling the truth about their own accuracy. This boils down to confidence calibration, which is a measurement of how closely a model's predicted probability scores align with its actual prediction accuracy. Perfect calibration means if an AI claims it's 80% confident, it is statistically correct exactly 80% of the time. What we desperately want to avoid is a model being dangerously overconfident in its own hallucinations. We actually evaluate this using what's called the expected calibration error. By grouping predictions into confidence bin intervals, we can weigh the differences between the average confidence and the average accuracy. For this data set, doing the math gives us a discrepancy score of 0.1377. The golden rule: the closer that number is to 0, the more we can actually trust the AI's stated confidence. Which leaves us with a pretty provocative final thought to wrap up on. If our models require such incredibly complex layers of quality estimation just to catch hallucinations, can we ever safely trust a completely sealed black box AI with zero oversight? It's something every developer and honestly every user needs to seriously think about. Thanks so much for joining me on this explainer.